You ever just stop and think about what's actually holding the universe together? I mean, everything from a single drop of water to the stars way out in the sky, it's all governed by these invisible forces. So let's dive into this hidden world and really uncover the secret rules that build our reality.
I mean, it's a huge question, right? What's stopping everything from just poof, flying apart into a cloud of individual atoms? Well, the answer is this constant push and pull that's happening on a scale so tiny, we can't even see it.
Okay, so to really get this, we've got to meet the two main players in this game. First, you've got your intramolecular forces. That's INTRA, as in inside. Think of this like superglue that holds the atoms inside a molecule together. Then you've got intermolecular forces. Inter, like between. These are more like magnets that pull whole molecules towards each other. And trust me, you absolutely need both.
All right, first up, let's zoom way in. We're going microscopic, diving deep inside a single molecule to get a good look at that superglue we were talking about. These are the powerful bonds that basically give a substance its identity. So right at the heart of every single molecule, you've got these incredibly strong forces. You've got ionic bonds, which are kind of like a transfer. One atom gives away an electron and becomes positive, and the other one grabs it, becoming negative. And boom, that classic opposites attract thing just locks them together. Then you have covalent bonds. These are more of a team effort. Atoms decide to share electrons, creating this super stable partnership. Put them together, and these bonds form the unshakable skeletons of, well, all matter.
And look, when I say strong, I mean it. This superglue is what makes water, H2O, water. Think about it. When you melt ice, you're just messing with the forces between the water molecules. But to actually break these intramolecular bonds, whoa, you need a serious chemical reaction to literally tear the molecule apart and turn water into something totally different, like hydrogen and oxygen gas. Okay, so that's the story inside the molecule. But what about the space between them? I mean, if all the atoms are locked up tight, what stops the molecules themselves from just drifting off into space, away from each other? Well, this is where a much more subtle but just as important little dance of attraction and repulsion kicks in. And this perfectly shows that delicate dance. See, when molecules are a little ways apart, there's this gentle attraction that pulls them closer. But if they get too close, their electron clouds start bumping into each other, and they repel each other with some serious force. And that repulsion? That's what gives stuff its solidity. It's literally what's stopping you from falling right through your chair. And that little dip at the bottom of the curve, that's the sweet spot, the perfect distance where the attraction is strongest.
Now, these forces between molecules, they're not all the same. It's not a one-size-fits-all kind of deal. They come in different flavors, you could say, each with its own strength and personality. So let's take a quick tour of the main attractions.
First up, dipole-dipole forces. These happen in what we call polar molecules, which are basically just tiny permanent magnets. They've got a slightly positive end and a slightly negative end. And just like the little bar magnets you played with as a kid, they just naturally line up, positive end to negative end, creating this whole network of attraction.
But wait, what about molecules that aren't permanent magnets? Can they play too? Oh yeah, they can get in on the action. So imagine the electrons whizzing around a molecule are like a swarm of bees. Just by random chance, for a split second, you might get more bees on one side than the other. This creates a temporary, lopsided charge, like an accidental magnet. And this fleeting little magnet can cause a chain reaction, nudging the electrons in a neighboring molecule to do the same. That's a London dispersion force. It's weak, it's temporary, but it's always happening.
Now, you might be thinking, okay, an accidental force sounds pretty weak. Does it even matter? And you'd be right, one of them is tiny, but you'd be totally underestimating the power of numbers. When you have trillions and trillions of these forces all pulling together, they become a collective powerhouse. I'm talking strong enough to take a gas like nitrogen and condense it into a liquid. That is some serious strength in numbers, right there.
And finally, let's talk about the superstar of the group, the hydrogen bond. Think of this as a special, totally souped-up version of a dipole-dipole force. It happens when hydrogen is bonded to a really electronegative atom, like oxygen, nitrogen, or fluorine. The attraction you get is incredibly strong. It's like a powerful, very specific handshake between molecules, and it's the secret ingredient behind why water has all of its amazing, unique properties.
Okay, so we've got the internal superglue and the external magnets. But this isn't just some abstract science lesson, right? This stuff matters.
These forces are literally the architects of our everyday world. They dictate the properties of almost everything we see and touch. Let me show you what I mean. Okay, check out this molecule. It's called a surfactant, and it basically has a split personality. One end is polar, which means it absolutely loves water, but the other end is nonpolar, so it hates water, but it gets along great with oil and grease. This two-faced nature, that's its superpower.
So here's how that superpower works in the real world. The water-hating tails, they dive right into a little droplet of oil. Meanwhile, the water-loving heads stay on the outside, hanging out with the water. The surfactant literally builds a bridge between oil and water, allowing them to mix. This is exactly how soap works to pull grease off your hands, and it's how your salad dressing stays mixed. Well, for a little while anyway.
And this principle is absolutely everywhere. The states of matter themselves, solid, liquid, gas, it all comes down to the strength of these forces. In medicine, they are critical for everything from keeping drugs suspended in liquid medicine to literally compressing powders into the solid pills we take. I mean, these invisible interactions are truly the foundation of modern chemistry, biology, and engineering.
So, the next time you see water form a bead on a leaf, or you shake up some salad dressing, you'll know what's going on. It's not magic. It's that elegant dance of intermolecular forces. And honestly, we've just scratched the surface of these invisible rules that build our entire world. So the only question left is, now that you know the rules, what would you build with them?